We got two classes today, one theory and a lab, back to back. We're going to use both of them to cover some math topic though. So in our last class we looked into renders like this. This is the video from our last class, that how we can set up material in Blender through the Blender render. See, internally what we are using right now is this Blender render, but there are other options as well. There is the Cycles render, which we will talk about later in the course. They are fundamentally different in how you set up the material and how the entire render is done. So what I'm talking about right now is primarily dependent on Blender render and many other render engines similar to this. This is where Phong shading model or actually the Phong reflection model, you'd see that in practice in most cases. So in today's class we'll see how changing these colors or the specular intensity color or the intensity, it affects the whole thing. What's the math behind it? Okay. One thing I want you to realize over here is when I make any changes, and let's say I export them to a wavefront OBJ object like we have done before. So let me just do this for this cube object. And in doing so, where is this? It should be on my desktop. We got two files, one OBJ file Okay, so this is the OBJ file where we have the vertices and the edges, and well, not the edges, the faces. We also got the vertex normals. We talked about these things before. What we didn't talk about is this material file, this cube.mtl. Okay, so if we open this up, this is what you'd see, that we have some material defined, and there labels like K, KD, KS, and we need to understand what these things are. Okay. Because they will define the color, the look, how reflective this is, how shiny this is, everything will come from there. So a few things to start with. Let us just look at this render. When it's a very basic render, we have a light that's illuminating from somewhere over here, because you know that there is light over here on this surface, but we don't see any light over here because there is nothing coming from that angle. If you look at the setup, the light is coming from here and there is no light on this side. That's why this appears dark, this part appears dark. Okay. The other thing I want you to notice about the light itself is the render looks like this, this is light brown or orange, whatever you call it, because the light is predominantly yellow, white light in here. But if you change the color to something else, to make it, let's say, a green light, the color of the render will be different. Or if you change that to a, say, purple sort of tint, the color of the render is going to change. So it's not just about the color of this material, the color of the light also plays a role. Okay. If you have a white light source, then the objects, they will show their natural color. But if you don't, if you have a different color, then everything will look different. So we need to take that into account, and we also got for each of these materials we got a setup where we can define the diffuse color, the specular color, and there is another component that's the ambient color. Okay. So these two things, the diffuse and specular, let us talk about these two things first. For the diffuse color, the sense is that you'd know the direction from where the light is coming from. So even in this render, you know that the light is coming from up top there and from a side, like from the right side, because this part is black. So we have a sense of direction. And what also matters, what I talked about in our last class, that let us assume that the light source is over here and light rays are coming up. Okay. So these things are brighter because, well, when the light reflects, the angle that it makes with the surface normal is actually smaller compared to something that's further away over here. So if we have an angle alpha and if we have angle beta, we'd know that alpha is actually smaller than beta, and this thing shines brighter compared to this part. Do we understand this? Okay. The more angle you create with the surface normal, the darker that part will become. Okay. So this is what happens in diffuse light. There is no shiny thing. You still have a gradual progression moving from brightness to darkness. Things will gradually fade away or move into darkness as your angle with the surface normal increases. Okay, and that's what I try to draw up there, which is also quite apparent in our real life. Let's say we have a flat surface. I mean, this is how our world appears if you look at it. Let's say we got a hut like this, all right? And the sun is coming up from here. Okay, so if it's coming from here, from total darkness, then right now the angle that it creates at any point is 90 degrees with the surface normal. This is the surface normal. When the sun is over here, for example, then the angle that it creates over here is less than that. When the sun comes up some more to, let's say, up here, then the angle that it creates with the surface normal is even less. Okay? And when the sun goes down, okay, so this is the angle that it creates with the surface normal. As the sun keeps on going down like this, you'd see that the angle is again increasing. So right from sunrise, what happens is that the angle that the sun creates with any given point, it can be any point over here on this world, at any given point, the angle is initially decreasing, and that means that the amount of light that we have throughout the day is also increasing till we hit noon. And after that, when the sun starts to go down, what happens? We start to lose light, and the angle also starts increasing because you're always calculating the angle with the surface normal. Can we say this? See, for any given surface, we know how to calculate the surface normal, right? Something that would stand right up there, we did so by doing the cross product of two vectors A and B. We know how to calculate the surface normal. So what I'm saying is that from any given light source, let's say the light source is over here, you'd have a ray that falls on to that point, and in order to calculate the diffuse part, we need to calculate this angle, because the smaller the angle is, if the light source was right here, then it would have the smallest angle. It would be right here, angle 0 degrees or 0 radian. That's when you'd have the most amount of light. I mean, this is what happens when the sun goes here. But if the sun is at a slanted angle, like this, the more angle you have, the less light you'd get. That's the only claim that I'm making, that you see that over here we have less of an angle compared to somewhere over here, because this is moving further away, so it'd have higher angle. I mean, this is probably even easier explained if you look at something like this. I mean, it's getting flattened out, right? The further we go away, the more the angle gets larger, and also it would become darker if you move further away from than that. Okay. So this is the effect that we see in diffuse reflection. We are not talking about the shiny component, but what we are talking about is light fading away, and that's why things will get darker as you move, as you increase the angle like that. Okay. The other thing that you need to notice is with the, let me bring up another mesh, the monkey mesh. And I'll just make it a little bit smoother. And create a material right here. Okay, and let us look at it as we change the material into rendered mode. So this is the rendered view. Okay. So if you look from different angle, the reflection right here, the shiny reflection is right now right here. Okay. But if I move the camera angle, see how this reflection shifts? Where's my light source? Yeah. So if I look at from a different angle, see, we see different points that are becoming shiny, and that's the nature of this specular reflection. But also what you should notice is that the light source also has a role to play, because if I change the light source, that's the rendered view. I can't see the lamp. Right. So the light source is over here. If I move it away to somewhere over here and then look at the rendered view, you see this is totally different, and the shiny thing appears over here. So for both the diffuse and the specular, the light source has a key role to play. This is what I want you to understand. Okay. However, for the last part, which we called ambient, let me write them down. What we are talking about, this is called form reflection model, and it has three different components for any sort of reflection. We already talked about diffuse reflection. We talked about specular reflection. And now the last thing is the ambient reflection, where you don't have any sense of the source of the light. It's just that there will be a very small amount of light that will appear from nowhere, and it will give you a very light reflection, but it will be there. And an example that I gave in the other section is something like this, that if you're in your room at night time and the power goes away, what would happen? Everything will become really dark, right? You won't be able to see anything. But as time goes on, in like 30 to 40 seconds, you'd start to see things because your eyes will adjust to the dark environment, right? Even if you don't turn on any emergency light, you'd see that because there will be a very small amount of light coming from somewhere in your room. It could be light coming through your window from another place, or maybe moonlight, or even your cell phone. Whatever small amount of light it emits, it will get reflected on the walls, on different surfaces, and come back to you. So that's not going to make everything visible, but you will still see a small amount of light, and through that you'd be able to understand where things are. And that also comes from the fact that you're in the room and you know where things are. Your brain will help as well. So it's a combination of everything together. So what I want to stress on is that for ambient light source, it's like ever present. You don't have the sense of the source. You don't know where the source is. You'll have a very dim light all across the scene. Okay, so it's a very small component. For the diffuse reflection, I spelled it wrong. For diffuse reflection, the idea is that the light will fade away and things will get darker as the angle increases. Angle with what? The angle with the surface normal. As the angle with the surface normal increases, the light will fade away and things will get darker. So for the final one, where we talk about the specular reflection, this is about a very shiny part which moves with the viewer, okay, but also the light source matters. So all these things you can see in Blender in the actual render. I mean, this part, this is clearly the specular one. Okay, we're in the live mode. So let me go and get a render of it. Let me lock the camera to view. Yeah, that'll do. Okay, so what I want to say over here, that if you look at these shiny parts, these are due to the specular component. So this is specular, okay? And this matte part that's not shiny, that's our diffuse. Okay, and through this diffuse thing, you'd see that you'd have bright parts. I mean, this is not so bright, but as the angle increases, as you move further away, things are going to get darker. This is not in shadow. I mean, shadows are something different. Here we have shadow. Well, not the whole thing. So over here you see that that's shadow, right? That's why this is black. But what we are talking about is more of a shading effect, that from brightness you go into darkness. Okay. And this is an interesting surface because you'd have different surface normals that are going in different ways because it's made out of a lot of polygons. It goes like that. And even without that, even in the small space that we got, things are brighter over here compared to how they are over here. Okay. Alright, so in today's class, we will look into the math aspect of it. We'll see how we can write this thing mathematically so that we can come up with pixels color. So if you look at any render for that matter, if I render this out one more time, you see over here are boxes, and these boxes, they have a specific color. They have different colors. And we study these things in image processing, that each of these things are called pixels, and pixels are made out of different color combination. There are many different color models. The most common one that we talk about is RGB. Colors can be made out of red, green, and blue. These three primary components. And for each of these colors, they can be described like that. And even over here, you see that they're all boxes. These are all pixels. Even if you take a photograph with your phone or any digital camera, if you look at the output, if you zoom it up enough, you'd see all these boxes. But from a distance, they don't look like that. They're much smoother. From this distance, for example, everything is really smooth. You don't even see the pixels, and that's why it's fine. So what am I talking about? I'm talking about that level of zooming where you're going to actually define what would be the color for each and every pixel. So this is the product of our work. Like, we got a model, we are going to render it out, we get a 2D picture, we get a JPG file or a PNG file, whatever be it. The file format doesn't really matter. It's just that the pixel colors, you need to define them so that you can produce something. So when we're describing this model, what are we describing the model with? Vertices and faces. We're describing this model as a polygon mesh. Now, how do we know that? Because this is what we saw in our internal representation, that if you look at this OBJ file, okay, all we got are vertices and faces. We can also have vertex normal, but that's a different story. We know how to calculate the vertex normals by doing the cross products, right? We learned how to do that. So right now, what we need to figure out is how we are going to color them based on just these information, the corner points, the vertices, and the faces, and also some description of what type of material it's going to be. Okay, like metal stuff will be different from, let's say, fabric or leather. They should look different, and we need to figure out a way to show them in that way. And even if it's metal, it would also depend on what type of metal it is. So there's a lot of variation in our real life. We need to model that in that way. So there are two different things. One is the physical aspect of it, where you define the geometry in terms of vertices and faces. And there's another aspect where you define the material itself. What's going to be the color, what's going to be the texture like, what's it going to feel like when you look at the object. And a Blender allows us to do both of them. Like, we can shape things up, we can edit the geometry, and we can also define the materials. These are the things we saw in our last few classes. Like in the last class, we were talking about the material over here. We played with these colors, the reflection effect and everything. Is this thing clear? So the ultimate target for us is to define the intensity of a pixel. We need to define the intensity of a pixel. That's the target. Okay, if we can do it for 1 pixel, like if I just hit render, if I can do it for 1 pixel, like over here, then I can do it for another pixel, and then I can do it for the other pixel. So whatever many pixels are there, we can do it for everything. Okay. So right now the target is to do it for 1 pixel. And notice that I'm using one particular term called intensity. However, when you're talking about a pixel, intensity can mean the red, green, and blue, all these different intensities. Okay. So if you take any picture, you can actually break it down into 3 different channels. If you take a RGB picture, you can break it down into red, green and blue, these three different intensities. And let me show you if I got GIMP installed. I don't. Shouldn't take too much time. And in the meanwhile, let me just get this picture in there. Image, save as image. Okay, we got GIMP ready. Okay, so this is our picture. I wanted to use this photo editing tool so that we can decompose this into three different channels. See, this picture over here looks colored picture, but over here we see only grayscale, shades of gray. Okay, and what I want you to notice is that this picture has some red parts, right? And some like purple tints, and there is nothing to be nothing green. So over here things are really bright. Okay, but if I turn off the red channel, this is the green component, which is really dark because there is nothing that much to be green. If I go for the blue channel, this is where the bluish stuff, they're bright. Do you see the difference? If I enable the red part, then the red parts are bright. If I go for the blue channel, this is where the blue things are bright. Is this thing clear? So if you're talking about the intensity of a pixel, it really means the separate intensity of the red, of the green and the blue. So any pixel can be represented as a vector where you're talking about these three things. So intensity of a pixel is actually the intensity of red, green and blue separately. Okay? So in other words, we can write it as, where is my cursor? Right here. So if I write intensity with I, this is nothing but IR, IG and IB. Red, green and blue. Three different intensities. Now what Phong suggested in his reflection model is that all these intensities, the red, green and blue, they can be computed, and if you can do it for the red channel, you can also do it for the green channel, and you can also do it for the blue channel. It's all going to be the same, calculated in the same way, and the intensity can be written as intensity of ambient reflection, intensity of the diffuse reflection, and intensity of the specular reflection. So these three things combined together will give you the intensity of a pixel. Okay. Now notice what I'm writing over here. I'm writing this as a vector, and over here this is an addition of three different components, and I'm not really talking about any particular color because they mean the same if you're talking about the red, green or blue. So what would really happen over here, let me make a copy of this, is that if I want to talk about separate color channels, the only thing that I would change, let's say I'm trying to find out the red intensity. Okay, I'll just write it in this format. and that would work for this part. So if I'm talking about the blue intensity, then I'll just do the same thing, but we will only do it for the blue channel, or we'll only do it for the green channel, and then we will get the green part and the blue part. Okay. But in essence, the reflection model itself says that if you're going to calculate the intensity of a single pixel, you calculate the ambient reflection part, the diffuse reflection part, and the specular reflection part. All three of these things separately. Okay? Is this thing clear? Okay. So let us look at these things in terms of the calculation, the actual calculation, what goes behind the scene. What we have in this scene is a light source, two objects, and a camera. Right? There can be multiple light sources. So one thing I want you to notice is that the color of the light that you're going to use really makes a difference for the final render. So right now they look one way, or if I change the color to something, let's say yellowish, then the objects will definitely look different, right? So that's one thing. And the other aspect is the energy level. If you have a light source with a really high energy, then things will look really bright. Okay. If you put up a lamp in your room, so the energy level will make a difference. Let me increase this and show you what happens. So we can increase the energy, and you see things are getting brighter. And if I hit render over here, definitely things are brighter now. So the higher intensity that you have for the light source, the brighter everything will become. So for the light, there are two things that you need to consider: the color of the light and also the energy of the light. Okay. So when you're talking about the light source itself, you're also talking about this thing. For the light source itself, what we do, we define it as S, and as you may have guessed that for the light source itself, we have three different parts. Again, the R, the G, and the B. Okay. So for simplicity's sake, what I'm going to do is I will drop the total case of R, G, B because they don't really matter. You're just going to add them as suffix and actually calculate them three different times. You calculate the whole thing for red ones, for green ones, and for the blue channel ones. So it doesn't really matter talking about these things now. We can drop this all together and just consider this intensity of the light source. So the very first thing that I want you to realize, how we can calculate this ambient reflection. This is going to be very simple. We write it in this way. It's going to be the intensity of the light source multiplied by the amount of light it reflects back for ambient light. This symbol, it's a Greek symbol. This is not P, this is rho. This rho A is the, let me write this down. So this is intensity of the light source, and this over here, this is rho. Rho A is equal to this is the coefficient of ambient reflection. Okay, and what happens over here for any given material, you'd have rho AR, rho AG, and rho AB. Okay. for any given color. And the same thing goes for the intensity of the light source. We have ISR, we have ISG, and we have ISB. So what really happens is that when you compute IAR, for example, you multiply ISR with rho AR. When you calculate IAG, for example, you multiply rho AG times ISG. Is this thing clear? This also relates to the material that you're going to define. You see over here, this one says Ka. Ka is this coefficient of ambient reflection, and it has three different numbers. This is for red, green, and blue, and right now it says that it's going to reflect 111. That means it's going to reflect the whole intensity of the ambient red component, the green component, and the blue component. And this is where I want you to look into other materials as well. I shared a link with you through the classroom. I did it in the other section. If you go to classroom.google.com, in your computer graphics classroom, see, there's this resource, ambient diffuse specular coefficient. If you go to this link, it's about defining materials. Each of these materials, they behave differently. So let us look at any of these materials. If you look at bronze, so if you want to define something, if you want any object to appear like it's made out of bronze, you need to set up these coefficients in this format. 0.212, that's for red, 0.127 for the green, and 0.054 for blue. Okay. People come up with these things through experiments, and it's not a fixed number. Like I can give you an example. Let's say if you got a gold ring, it's not going to look the same as it wears out, right? With years, it's going to lose its polish, and you can polish it, and it will shine differently. So, depending on the nature of this material, it would still vary. So we have a reference number for gold, but it's not going to look the same. You can change these values somehow to make it appear a little bit darker or a little bit brighter, depending on how it is. Now, you can consider these to be the default values or reference values to start with. Then you can play with the numbers a little bit to get your desired effect. That's what I want to mean. So for the ambient part, if you're just looking at the ambient columns, we have three columns over here, red, green, and blue. This is what it says, that it's going to reflect that amount of light. So for example, if you look at black plastic, it has zeros there. What does that mean? That it's not going to reflect anything, right? And it's going to appear really black, really dark that way. It does reflect specular light. Since this is plastic, it will have some reflective property. It will shine, but it's not going to look bright. That's what it is. So for all these different materials, I mean plastic over here, you'll see that it doesn't really reflect that much of ambient light, but there are other components. It works well with the directional light source. For ambient light, what we said is that the direction of the light source doesn't matter. You have no sense of direction where the light is coming from. So the easiest way to calculate this is just you take this number, rho A, you multiply with the intensity of the light source. Once this is done, you get the intensity of that pixel. And you do the calculation 3 different times. Once you do it for the red component, the green component, and the blue component. Okay? So, to sum it up, let us just look at a concrete example. I hate this. let's say pixel color, and I'm just talking about the ambient part. Alright, so what would be the pixel color of a pixel which is representing a bronze material under a yellow light source? If I want to figure that out, what would I do? First of all, I need to know what's the intensity of the light source, right? That's IS. And IS will be defined by 3 different colors. There's a light source, it has a color, and we're saying that this is going to be yellow, right? This is yellow. If you mix red and green, then the color you get is yellow. Okay. And if you don't trust me, you can play with it over here. Let me just add a new material somewhere, or I can also create a new material over here. So if I put 1 for red, 1 for green, and 0 for blue, see, I get yellow. This is what it means. What I want you to understand is that if you put lower values, not 1, if you put, let's say, 0.5, if you put 0.5, this is still yellow, but slightly darker tone of yellow. Oh, it didn't work. Yeah, slightly darker tone. If I reduce the number, let's say 0.2, see? It's getting darker. But it is still a shade of yellow. So 110, that's really bright yellow. And if you reduce the red and green component, then it's still going to be yellow, but a different tint of it. So if I define the intensity of the light source in this way, what I need now is the rho A value. So let me write this down. Intensity of the light source and the rho A value. I need to copy that from this place. Where's this? 0.21, 0.12, and 0.054. So we're going to write them down. Okay. Now you're going to find the ambient component. That will mean the intensity of the light source, the intensity of the ambient light part is going to be 1 times 0.21, 1 times 0.12, and 0 times 0.05, so that's going to be 0. And these are going to be, if you multiply with 1, this is what you get. And if you have smaller component for red, green, and blue, whatever you have, if you had 0.5 for that, you just multiply with this. So what I mean by this is, let's say, let me change the values. If I had 0.2 here and 0.2 here, really dark yellow, then I would have 0.2 times this, and then 0.2 times this. Is this thing clear? So for any given material, I mean, depending on the material type, if you know the color of the light source, you can calculate the ambient reflection, because it doesn't really depend on the light source position or whatever angle it's making. It has no sense of direction. It's present everywhere. It's a very small component. Is this thing clear? So this is what we do with the ambient part. The diffuse part is where things start to get interesting. So let me draw a very crude picture over here. For diffuse reflection. Let's say we got a flat surface like this. Okay. And it can also work for curved surfaces. It doesn't really have to be flat. It's just that if you look at any of these models, I mean this monkey face, it looks really smooth and it looks curved, but if you look at the actual model, we have flat faces. It's made out of polygons, so we have flat faces. We have these quadrilaters which are really flat, like papers, and if you join a lot of them together, you can get this curved face. So we did this already, right? We can understand that even curved faces can be made out of flat things if you have enough of them. What I want you to understand is this reflection model. So right over here, let me come up with a setup. Let's say we got a point for which we're going to calculate the reflection, and there is some sort of a light source somewhere. Okay, so we got a light source, and let us call this light source L. Okay, so what's going to happen is that light will come from this light source, fall on P, and then bounce off, right? It will reflect. And when it reflects, it needs to follow the law of reflection. So we need to calculate the surface normal, which we know how to do already, right? And then finally it's going to reflect back with the same angle. So whatever is the incidence angle is going to be the reflection angle as well. Is this thing clear? Now compared to this, if we have a slightly different setup, let me make a copy of this. Okay, if we have a different setup where the light source is over here, then what's going to happen is that it will create a larger angle over here with the surface normal, and it will bounce off, leaving a smaller, a larger angle as well. Okay. And if you move this point to over here, again, you'd see that it creates a larger angle compared to this part if you move away. Okay, so if the light source is over here, you can sort of say that we'd have more light in this region compared to if you scatter away, like if you're moving away from this. These parts, they will become darker. These parts, they will become darker compared to what we have over here. Okay, this is exactly what happens in real life. Like if you're walking on the road at night, and if you have the sodium lights, you'll see that we have very bright light right in the middle, and then it goes away really fast. So that's sort of a diffuse effect that you can see even in this picture. So we need to model that somehow. Okay. Now if you look at this picture, we know P, we know L, because these things can be read from the description of the scene itself. Okay, you know where the light source is placed. Okay, do we know that through Blender? Yes, we do. I mean, even in this 3D modeling tool, if you click on this lab and go up here on the Properties tab, right off on the top corner, it gives you the X, Y, and Z values. And for those of you who are at the back, let me zoom it up a little bit. See, X equal to minus 2.89, Y equal to 1, and Z equal to 5.9. That gives you the coordinate in a 3D world. And if you're talking about this room, for example, this is also a 3D world. We can set up any reference point. We can say that the corner point down there can be our origin, and over here this can be our x-axis, going up can be the y-axis, and going towards you can be the z-axis. So we can set up any point as the origin, and from there we can measure the distance. Let's say if I want to measure the point over here, it will have a x, y, and z. So anything can have these 3D coordinates, and we can measure them. So if I consider that to be a light source, I can actually measure with a scale and say what's the x coordinate, what's the y coordinate, and what's the z, which we can do for that particular point. And if I'm talking about this point, I can know the x, y, and z values just going into the edit mode, and I can read out all these things. The same thing goes for each and every point over here, so we can know the coordinate, the x, y, and z values over here. So that's to say that I can know x, y, and z values for P. I can also know the x, y, and z value for L. This is known. Do we know this thing? The surface normal, do we know this? Yes. I mean, even if it's not given to you, you can actually calculate that by doing a cross product. Okay, that will give you the surface normal. So the question now is, since we know P and since we know L, do we also know this PL vector? Or let us just call this the L vector that goes from point P to the light source. Do we know this? Yes, we actually do, because this L vector is nothing but L minus P. Okay, and we have done this in our last class, that if you know this point and if you know this point, let's say this is V2 and this is V1, A will be V2 minus V1. And we have done this before. So we know L, we know M. How can I find out this angle I? I need to know angle I. Why? Because the smaller the angle is, the more amount of light we're going to get, and the bigger the angle becomes, we'll lose light. Okay, the highest the angle can be is 90 degrees when you have no light, and anything beyond 90 degrees you'll also lose light. Okay, so how do you find this? If you know two vectors, what's the internal angle between them? Is the question clear? Let's say, I mean, forget about this point. Let's say we got vector A and vector B. I want to know what's the angle over here. How do we find this? Well, there are many different ways of doing this, and even in the product ways, there are two different ways to find out the angle. See, if we got two vectors A and B, A dot B is, nope. That's a dot product. Is the dot product a vector or a scalar? It's a scalar. Dot product's a scalar because this is a scalar component. This is a number. This is the magnitude of A, magnitude of B. So you get two scalar values. Cos theta, again, is a scalar thing. So if you multiply all the scalars, you're definitely not going to get vector. There's another way to do this. If you do cross product, the magnitude of the cross product, not the cross product itself, the magnitude of the cross product can be written as AB sine theta. Okay? So let us look at a very concrete example. Alright? Let's say A equal to 2, 1, 5 and B equal to 3 minus 2 and 6. These are two different vectors. Okay? I want to find out the angle between these two. How do we do that? So if you go the dot product route, this is the easier one, because in the cross product one you'd have to calculate the determinant, and after that you'd have to calculate the magnitude to go for the second part. Now the dot product thing is actually easier. Why? Because let us take this formula right over here, and what I can do is I can take this part and put it underneath. Okay? That helps because now you can write cos theta equal to A dot B divided by magnitude of A divided by magnitude of B. So if you're looking at this problem, and I think I need to go to the other page. Yeah. So let me drag things over to the next page. This is the setup. This is what we got. How can we find out cos theta now? First of all, I need to find out the dot product. I mean, we are back to the same problem. So is there another way to calculate the dot product? For any given vector, let me write it in this way. We want to find out A dot B, right? This can be found out with AX times BX plus AY times BY plus AZ times BZ. If you talk about the three components as X, Y, and Z, this is how you can find out the dot product. So if this is what it is, tell me what would be the value for A dot B in this example.
Minus 2.
This is going to be 2 times 3 plus 1 times minus 2 plus 5 times 6, right? And that's equal to 6 minus 2 plus 30, which is how much? 34? Okay. Is this thing clear? Calculating the dot product is really very easy. You go for all these components, multiply the components individually, add them up. However many components there is. So this is 3D vectors, that's why we do it in this way. If it were 10D vectors, no big deal. You do it for 10 different times, you add the results. Okay. So now we know this part. Do we know how to calculate the magnitude of A? The magnitude of A is going to be, oh by the way, I really need to put bars over here, which I'm not doing to save time, but whenever you're answering this, you need to make sure that they look like vectors. Put a bar on top. Okay, so the magnitude of A, how do we find that? Square root of AX square, right? Plus AY square plus AZ square. This is how you find out the magnitude of any vector. So for this particular vector 2, 1, 5, what is it going to be? Square root of how much? 2 square, which is 4, plus 1 square plus 5 square, which is a square root of 30. Okay. What about b? It's going to be square root of 9 plus 4 plus 36. And you said 49, right? Yeah, 49. That's exactly what it is. So we got the magnitude of these two vectors. Can we put everything together to find out cos theta? Cos theta now is going to be 34 divided by square root of, well, let me calculate these values. Why do I do it this way? We got 34 divided by two things. 34 divided by square root of 30 times square root of 49, right? And that's what's that? Well, yeah, they will come over here. This is square root of, let me write this. What I got is 34 up here, and in the bottom part, we got two things. One is square root of 30, and the other one is 49. Over here? Why do I need that? No, the other problem, yeah, that was a different issue. I wrote it with X. And they have a slightly different symbol. That's why I failed. Okay. 0.8867, that's the result. Okay, so now we can calculate this. And can we calculate the actual value of theta? Yes, cos inverse. So if you go into the advanced mode, you can just go for cos inverse. Where is it? Yeah, thanks. It's just that okay. That's the inverse. Probably that's how you do it. Okay, so I get 27.52. I mean, probably you're set for, I'm set for degrees. Depending on the mode, whether you're going for degree and radian, you'd get the result. These things all should be calculated in terms of radians by default, unless you want to do something special. So this is actually cos theta, and there is a good reason why you don't want to find theta from here. We just keep theta inside cos, like we will deal with cos theta as it is without changing anything at all. Okay. Is this thing clear? This whole calculation, how you can do this? This is for any vector A and B. And if you understand how to do this, you should also be able to do it for this L vector and the N vector. Is this thing clear? Let me know if you got any problem. We can define a vector L that goes from P to L, and we already know the surface normal, so these things are known, and we can find out the angle I, the incidence angle between these two vectors just by doing dot product and dividing the dot product by what? The magnitude of L and the magnitude of N. N being the surface normal. Now once you do this, what would be the next step? I mean, why would I want to keep it as cos I, not get I out of it with cos inverse? The reason being, I mean, you need to understand what's happening over here. The bigger this angle is, the less amount of light we will have. The lower the angle is, the more amount of light we will have. This is what we've been saying for a while now. So what really happens in real life? Let us consider the effect. Let's see, Dhaka sunrise, sunset. So yeah, 6:32, that's when the sun rises, and 5:53, that's when sunset. So it's more like 6 o'clock and 6 o'clock. It's a little bit shifted. Let me write this down. 6:32 and 5:53. So this is for sunrise, right? Okay. So at what point in time would you have the most amount of light throughout the day? Somewhere around 12 o'clock, right? What about 11 o'clock or 10 o'clock? Well, at 12 o'clock, obviously, that's the highest amount of light you're going to get. But even at 10 o'clock or 11 o'clock, there's still plenty of light. Okay. If you talk about the 6:32, as sun is rising, I mean, it's still pretty dark. Sun has just come up. At 7 o'clock, what's going to happen? We'd have enough light. It's going to be dark, well, but we will have enough light. It really takes little time after sunlight, after the sun rises, for us to get light. Okay, by 8 o'clock or 9 o'clock, everything will be visible, right? I mean, there is no darkness. I mean, even at 7 o'clock, literally, there is no darkness. If sun rises at 6:32, and if it's not really cloudy, then you'd have plenty of light right there. If you look at the other side of the spectrum, when sun sets down at 5:53, okay, you're going to lose light really fast. After like 5:30, you're going to lose light really fast. In like 20 minutes, you will have lost a lot of light. But if you look at from 3 o'clock to 5 o'clock, yes, it's going down, but it takes time to lose the light. So what I mean to say is that it's not really like if you say that this is sunrise, and it's at noon, the light is going up in this fashion and it's going down in this fashion, in a sawtooth. I mean, you see these sort of waves in digital logic design or computer architecture when we send our class. This is called sawtooth, right? It has a sharp rise and sharp fall, and you have a crisp edge like this. We're not talking about a wave like this. It doesn't go up like this and fall down like this. It's more like a smoother version, something like this. And that's why it's important to understand that after sunrise there is a sharp rise, and at sunset there is a sharp fall, but over here it's pretty flat. So if I were to say that, let's say from 6:32 to like 7:30, there will be a sharp change in terms of light, but after that the change is not so much. It's mostly flattened out. Okay, but over here, if you model it like this, that at 6:32 that's when the sun rises, and somewhere at like 12 o'clock, this is where you get the most amount of light. It's going to go gradually up like this in a straight line fashion, and it's going to fall down. That's not going to happen. It doesn't happen in real life. What happens in nature is that nature understands that things need to be done in a smooth fashion. Let me move this out. So this is what happens in nature, and nature actually follows something we study in mathematics. I hate this thing. Well, let me borrow this from somewhere. Let me draw this properly. There's a graphing tool, FooPlot. I can go and ask them to draw a curve for you. Okay. We know cos x, right? We know the cos curve. This is how it behaves. At 0 radian, what's the value of cos? 1. And at pi by 2, which is also 90 degree, cos is going to be 0. At negative pi by 2, what's the value of cos? That's also 0. This is pi by 2, that's 0. And over here, this is minus pi by 2, negative pi by 2. That's where also cos is 0. Okay? And down here, at pi, cos is minus 1. The cos value ranges from minus 1 to plus 1. It oscillates between that. Okay, it goes up and down. Okay. So why are we talking about this cos curve here? Because this is what we are interested in this part. Say this is where the cos curve will lie. It's going to be like, let's say this is positive 90 degree, and this is going to be negative 90 degree, or pi by 2 in radian, and this is where we have 0 degrees. Okay, do we find the same thing in nature, that when you have 0 degree angle, this is where you have the most amount of light, and when you have no light, that's when it's going to be 90 degrees on both sides. Okay, so this is to say that at 0 degree, I want 100% of the light. When it's at 90 degrees, I want 0% of the light. If it's at minus 90 degree, I want 0% of the light. Can we say this? Okay, so if that's the case, then the cos theta value is a very useful thing, because it can readily supply us what percentage of the value we are going to take. At noon, when the sun is right up above our head, we have 0 degrees. That's when we see everything. That's when we have the biggest contribution. And right at sunrise, we don't have anything. Sun is just coming up. That's when we start to see things. Okay? And down here, I mean, if you're going to follow the cos curve, things will go into negative. That's something we cannot afford. We will need to fix that somehow. But we are mostly interested about this part right here. That's what we see in nature. Okay? So we're pretty much at the end of the class today, the first one. I want to take like a 10 minutes break, and then we will continue with this thing. Okay, we're not going to go for anything with Blender today. We need to set up this mathematical model, and these things will be in your midterm exam as well. There will be some question along this line about calculating the ambient or diffuse or specular reflection, and also calculating the surface normal, because it's a part of the process. Okay, so we'll look into some other example, and hopefully we will finish the specular one as well. Any question about any of these things? No?